Okay, if you're ready, let's just begin. If you look at these columns here, these are the columns of the current basis inverse. Why is that the situation? Because when you look at any tableau, what you have in the tableau is you've got the non-zero column for Z. You've got the reduced costs defined by CB, B inverse. That's a row vector times A minus C. That's your reduced costs. But this part is B inverse multiplying the initial A matrix. And of course, this part is B inverse multiplying the initial right-hand side. And this part is CB, B inverse B. And if the initial basic variables are, if the columns for the initial basic variables form the identity, then A is of the form identity for the first M columns plus some other stuff in the remaining columns. Okay? In which case, of course, B inverse A gives you B inverse times identity, so it makes a copy of itself where the identity was at the very beginning, and then B inverse A cap. So B inverse is that part, Y1 through Ym. Okay? Now what do we do with these columns? I separated out these columns because we're going to use those columns for tie breaking. Okay? So I'm going to erase this stuff. This was just side information for you. Let me erase that. This is my entering column. So what we do is we initially use the current right-hand side column to identify those row indices which qualify for the minimum ratio. So I sub 0 is the set of row indices for which the minimum ratio is attained. So let me write that down. It's the set of row indices R such that YRK, no, BR, sorry, BR over YRK, the rth element of the YK column here, is one of the minimum ratios. Where the minimum is taken, of course, over I, for which YIK are positive. Okay? So I0 is a set of row indices which qualify for the minimum ratio. If I0 is a singleton, there's nothing to do. You just make that particular rth basic variable exit. Okay? There's only one qualifying candidate. If, on the other hand, I0 contains more than one indices, so if the cardinality is more than one, then form I sub 1, which is the set of qualifying indices associated with the first column of B inverse. So I sub 1, how do you form that? What you do is the following. You restrict your attention to row indices that are already in I0. These are the tied ones. Of those, you look at the ratios of those with the elements, the corresponding elements of the first column here, and then you choose the minimum ratios relative to that. Okay? So the formula for that is the following. I1 is the set of row indices such that YR1, the element coming from column 1, divided by YRK, the element that comes from column K, is a minimum ratio over those row indices I, YI1, divided by YRK, where I is restricted to the initial tied elements, I belonging to I0. Okay? So, the element from here divided by the appropriate element from the entering column. The entering column elements are always the divisors. The numerators are either coming initially from I0 or from here in the second one. So you do this. If it turns out that I1 also has more than one element, you form I sub 2. Which is, of course, the set of row indices R such that YR2, now we're looking at the second column, divided by YRK. The denominators are always coming from the entering column. These are the minimum ratios, YI2 over YIK, where in this case I is restricted to which? I1. Okay? So each time you're getting smaller and smaller, etc. You keep doing this until finally the last one is I sub m. Maybe before that you will obtain a set which gives you a single element, in which case you exit that. Otherwise, you arrive at the last one. In that case, that must supply a single ratio. Otherwise, some two columns of the columns, well, let's put it this way. The columns of B inverse are linearly independent, so they cannot be proportionate, which implies that you must definitely get to a single element set at the end. So that's the initial. From here, you compute I sub 1. From here, you compute I sub 2, so on and so forth, I sub 3, etc. And finally, I sub m. And finally, you get to your single exiting variable. And that's the... Now, the justification of this is how the method is implemented, which, of course, takes some additional computations in each iteration. Nevertheless, it works. Now, why it works requires justification. In other words, you need a proof. And in that case, you need to give lexicographic arguments. So you need to define what lexicographic ordering means. You know, one vector being lexicographically greater than another vector, so on and so forth, which I'm not going to get into because they are already settled. So let's not bother with that. We have more important stuff to cover during the course of the semester. Okay? But read your book. The book does a good job of explaining all that, so do read that. And of course, not everything is covered in class, but you're still responsible knowing that stuff. Okay? So don't avoid that. Okay. Now, the last thing is Bland's rule. This is a very elegant rule in my judgment. It simply says that of the qualifying elements for entering variable, you choose the one with the smallest index. And of the qualifying elements for the exiting variable, you again choose the one with the smallest index. Okay? So choose the smallest indexed variable among all non-basic variables. MB stands for non-basic. Among all non-basic variables that qualify to enter, which means these are the variables that have positive reduced cost for a minimization problem. And for a maximization problem, they are the ones that have a negative reduced cost. Okay? We're not talking about the most positive or the most negative. We are talking about those that qualify, which means they either have positive for minimization or negative for maximization. So you should make a note of that probably, because a lot of people seem to misunderstand that particular rule. And for entering variables, for exiting, you choose the smallest index again among tied ratios, if you have ties, okay, for the exiting variable. By the way, the lexicographic rule or the perturbation rule or perturbation method, they only pay attention to the ratios. They have nothing to do with who to enter or which variable to enter. Okay? It's free. So in the lexicographic method, you can choose, for example, the most positive reduced cost still. Nevertheless, in this Bland's rule, you encounter the first variable that prices out favorably, which means it has a reduced cost which is positive for minimization, and then you choose that one. Okay? So, all right. Any questions on these things? Because I'm going to finish up with cycling stuff here. We begin the revised simplex method. Okay? New topic, fresh minds. Hope. I wish we had a morning class, because in the morning everybody seems to be better equipped, you know. But in the afternoon, for some reason, people start losing interest after a while. Anyway, you seem to be maintaining your interest much better than many other people that I've seen before. Now, in the simplex method, whenever you need to enter a variable, you need to inspect the columns for non-basic variables. In the revised simplex method, you don't have the columns for the non-basic variables. You just put them, you know, aside. You just compute them on a need basis. Okay? So, the tableau you've got is a much smaller tableau in terms of number of columns. You still have your Z column, which is a decoration. You've got your right-hand side column. And you've got Z bar and B bar for those. You've got B inverse here. You just keep track of what B inverse is. Okay. And then we have the so-called W vector here. Actually, let me just erase this. We don't need that. Okay. So this is the information we carry. The W vector is the so-called CBB inverse. Okay. It's a row vector, because CB is a row vector, B inverse is a matrix anyway, it's a row vector. So you've got this information. What we need to do is, we need to compute the reduced costs first to identify some entering variable if there's a qualifying one. Okay? So to compute the reduced costs, well, the reduced costs for the basic ones are always 0. So all you have to do is to compute the reduced cost vector for the non-basic parts. And for that, the definition simply says that you take the W vector CBB inverse, multiply it with the columns of the non-basic variables, and subtract from it the non-basic costs, or the vector of non-basic costs. So you compute this. If there exists some Rj which is positive, again for a minimization, or negative for a maximization, then enter that variable. Let's make this k. Okay. If there is a reduced cost which is positive, then enter the variable xk. If you go with the Bland's rule, for example, this is the smallest indexed one, okay, that you have positive. All right. Then, all right, so once you decide to enter xk, we need to compute the vector yk. Compute yk, which is defined by the current inverse times the original column ak. Okay. AK is, of course, stored somewhere. And write the new column with RK at the top, that's the row 0 element, on YK in the lower part, next to the tableau. So what that means is you write this here as a new column. See, all the non-basic columns are out of sight, but then you simply pull one of them into sight. You see it now. This is the one associated with xk, and you've got your yk here, and that's your entering column now. This comes later, so make sure you've got that sequence. You know, things some of this stuff come later. All right, what is the next step? The next step is to look at the ratios of the B bar with positive elements in the entering column, and then identifying exiting variable. So compute the minimum ratio using the column yk using the positive yiks and pivot on YRK to transform the tableau. Of course, when you pivot on YRK here, B inverse is now transformed into the inverse of the new basis. The new basis is different in one column. Okay? And of course, W is also transformed. So you've got the same information relative to the new basis now. So everything is well updated. And then you just continue to do this until what? Until your reduced costs for the most recent tableau happen to be all less than or equal to 0 for minimization. Okay? That's the termination criteria. So what is the advantage of this? Well, the advantage is you don't have to deal with a lot of unnecessary columns here. It's really nice in that sense. Nevertheless, computationally, the simplex method in the regular form and this one, they are essentially the same. There are some minor differences in computing effort. Nevertheless, in the worst case, they always give you the same effort. Okay? So, but it's nicer at least for hand or for conceptualizing what's going on here. And this way of attacking the simplex, or this way of handling the simplex operations is especially useful when you have too many columns. If you have zillions of columns, in that case, of course, you're avoiding that situation. And that will be the case when we look at certain problems that require column generation. Sometimes you end up with a linear programming problem whose columns are too many. Just you can't handle that. In that case, you want to deal with them implicitly in a different way. And so anyway, when we get there, this will be quite handy, actually. Let me give you an example here. All right, so we will begin with x3, x4, which means that the initial basis is identity. This is the same old problem that we worked out before. And so the initial tableau is really simple. It's got the B inverse here, which is 1, 0, 0, 1. 6, 8, 0. The reduced costs are 0 and 0. CB, B inverse, or your W vector here is, CB is the 0, 0 vector, because these are the slack variables. The initial basic variables are the slacks, times B inverse, of course, gives you 0, 0. And the objective value is certainly 0. Okay? Okay. So, then we compute the reduced costs. And so let me just do it in the form WA minus C. You can restrict it to only non-basic variables, but that I have to fetch them. So anyway, I'm going to use 0, 0 here for W. And then, of course, WA, well, it doesn't really matter what A is here because it's going to be 0 anyway, minus C. So this will simply give you the minus C vector, which is what? What is the minus C vector? Plus 1, plus 3, 0, 0 with a negative in front of it. No, actually, no. It is this way. Okay? And this is a minimization. So the most positive one happens to be the second one, which tells you that enter, x2 should be entered. Okay? Then compute y2, which is B inverse A2, but B inverse is identity in this case, so it simply gives you A2, which happens to be, what is A2 here? 1, 2. That's your Y2 column. And you take it and write it next to the tableau. The top element is R2. R2 is 3 here. And then you've got 1 and 2. That's the entering column. You look at the ratios of 6 to 1, 8 to 2. The second one is smaller, so you pivot on that one. And then we get the new solution. By the way, the basic variables were x3 and x4 here. Now we have x3 and x2. This is my new basis inverse. And these are the new values of the basic variables, with minus 12 specifying the value of the objective function. So we compute again the reduced costs. In this case, W is 0 minus 1.5 times the A matrix, which happens to be 1, minus 1, 1, 2, 1, 0, 0, 1, minus C vector, which is what? Minus 1, minus 3, 0, 0. And that will give you, I don't know, minus, that's going to be 1.5. This will be minus 3. Second, that one will be 0. This will be minus 1.5. Minus 1, minus 3, 0, 0. And that gives you 2.5, 0, 0, and minus 1.5. Yes. And this one, of course, is the positive one, so you enter x1. That's what it says. Compute y1, which happens to be inverse 1, 0, minus 1, minus 0.5, 0.5 times A1 column, which is, what is that? 1 minus 1. So the result of this is how much? 1.5 and minus 0.5. Yes. So you write it here. With reduced cost of 2.5 at the top. Compute the ratios. Well, there's only one ratio to compute, so that one exits. So that's the one you pivot on. So we get to the new solution. After the pivoting, what we have is the following. 2/3, 1/3, minus 1/3, 1/3, 4/3, 14/3, minus 5/3, minus 2/3 at the top, and minus 46/3. You compute reduced costs again. Let's do it with one at a time this time, you know. R3 will be W times A3. What is A3? 1, 0. That's your A3. Minus C3, which is 0. And how much is that? I don't know. That will be minus 5/3. That's it. Minus 5/3, right? Yeah. R4, which is the next reduced cost for the non-basic variable, is going to be the same W times 0, 1 minus 0 again. That will give you minus 2/3. And R1 and R2 are, of course, 0. You can verify that numerically if you wish. And, of course, in this case, optimality is concluded because all the reduced costs are non-positive. Okay? Optimum is reached. So this was a little bit simpler, I think. Okay, so in the initial description I gave you for the revised simplex method, we used pivoting in going from one tableau to the next one to update the inverse matrix. But typically, that's not what people do. In implementations, usually it's the product form of the inverse that is used for computations. So let's go into that. So let's assume you have a basis B and some rth column of basis B is to be replaced by an entering column. Okay, so suppose the rth column of the current basis B is to be replaced by an entering column A sub k. Xk is the entering variable, Ak is the column associated with that. So after the replacement, the resulting matrix, I'm just going to refer to it as B cap. And our job is to compute B cap inverse because we work with the inverse matrices. How do we do it? Without pivoting, that's what we're going to go into right now. Okay? So first compute the usual Yk column, which is the current inverse times Ak. Of course, we assume the current inverse is already available. Okay? And then we define an elementary matrix, elementary vector eta. Eta has elements eta 1 up to eta n, eta m, sorry. Let's also put eta r here. Eta r is defined in a special way. All the other ones are defined in a similar way, where all the components except the rth one are simply defined by the negative of the element in that row. In other words, for example, for eta 1, you look at the first element in Yk, take the negative of it, divide it by the pivot element. Yrk. You do this for each one. Except the rth one. The rth one is simply 1 over Yrk. So you still divide by Yrk, but you've got 1 here rather than something else. It's not Yrk, okay? It's not minus Yrk, okay? There's nothing mysterious. You seem to be looking a little bit bewildered. Huh?
Will we convert to 1? Will we do some operations to obtain 1, or just directly?
No, all you do is you compute yk, and then you identify yrk, and you know yrk because you know that the rth column will be replaced by ak. So yrk is the rth element in the column yk. Okay? So you take that, you use that as a divisor. Okay? And the top elements or the numerators are the negative of the elements you see in yk, except for the rth one, which is just 1. Okay? That's it. All right, so this is easy to form. Then we define an elementary matrix, E, which has the identity columns except in the rth column. The rth column is the eta vector. So this is simply the identity matrix with the rth unit vector replaced by the eta vector. Okay? So this is the rth column of the identity, except that it's replaced now. And it turns out that the inverse of the new matrix, B cap, is simply the elementary matrix E times the old inverse. You can show that. It's really simple. So how do we use this? We begin with the identity. So B0 is the initial basis matrix, which is the identity. But it need not be the identity, but it's just the initial basis. So if B0 is the initial basis, and if we simply define E sub I to be the ith elementary matrix corresponding to the ith iteration, what elementary matrix? Well, elementary matrix that I formed like this, except that from one iteration to the next one, of course, this changes one column at a time. Okay? Then, of course, the inverse in the ith iteration is going to be the elementary matrix E sub I times the previous inverse, the one in the I minus first iteration, which is going to be EI times EI minus 1 times BI minus 2, so on and so forth. So if you just keep doing this, you get EI, and then EI minus 1, so on and so forth. You just keep going. And then finally, the first one, multiplying the initial inverse. So first this is found, and then E2 times that is found, so on and so forth, and then this is found. And then anyway, this is the way it goes. Okay? you get the idea, I guess. This is already computed in the first iteration. In the second iteration, you get E2 times what's inside here, so on and so forth. So it just keeps going like that as you move along. And if the initial matrix happens to be identity, of course, you just get rid of that as well. Okay? It's just the multiplication or the products of the elementary matrices. Now, this is really useful for numerical purposes. See, this stuff avoids numerical difficulties which might be associated with taking the inverse all the time. Because in inverses, you've got lots of fractions, you divide a lot of numbers, and after a while, you may start running into numerical instability problems or numerical inaccuracy problems. Whereas this one is simple matrix multiplications. So let me just point out a few things here. For example, let's just look at pre-multiplication by an elementary matrix. If you have a vector C, and if it pre-multiplies an elementary matrix E of the form I gave you, this is simply, well, it's almost C itself, except that there's one bad column here. So you've got C1 up to Cn multiplying this one, in which case Cm will multiply that, and then Cm will multiply that, so on and so forth. So this is simply the same vector, except you have the dot product of Cn eta vector in the proper position. So you don't really pre-multiply. You just make a copy of the old vector C, except that the rth element, this is of course the rth element, assuming that the bad column of E is the rth column. Okay? You simply replace the rth cost here by the dot product of Cn eta. That's really simple stuff. Let's look at also post-multiplication. Why am I bothering with these? Because we use both pre-multiplication and post-multiplication in the revised simplex method. Okay? So if you post-multiply a vector A by the elementary matrix E, this is, how does that work? So A is a column vector here. Well, whenever you run into the rth column, of course, you multiply it with the appropriate elements here in the eta column. So what you do is, you can view this as the following. You can take the A column with a 0 in place of the rth element, so this is the rth one. And then add to it the element A sub r times the vector eta 1 up to eta m. So again, this is simple stuff. You take the first, you take the A vector itself, except the rth element is now 0. You add to it A sub r, the rth element of the A vector, times the eta vector. That will give you EA. Okay? If you don't believe me, you can work it out at home and convince yourselves that that is the case. So here's the revised simplex method. with product form. So let's assume that the initial basis is the identity, and suppose we stored the elementary matrices. E1 up to EI after the ith iteration. Now again, you should not literally take a storage for each E1 or EI. What do you need to store EI or E sub j, whatever? You need only two pieces of information. The rth column corresponding to that particular elementary matrix. So you need only one number, r, okay? And you need a single vector, which is the eta vector. So just one number plus a vector is enough to store all this information. So if you call r sub I the one corresponding to the ith one, and the eta vector corresponding to the ith iteration, you just need to store these numbers, or this number and that vector, okay? The current basis inverse is simply EI times EI minus 1, etc. up to E1, because the initial matrix B0 is simply your identity. We're just using this formula here. And given this, what we do is the following. Calculate the current basic feasible solution xb, which is your B inverse B, by the following, by the formula xb equals, well, in place of B inverse you write EI sub 1, EI minus 1, so on and so forth, E1. And then the entire thing multiplies B. So, first you multiply B by E1, and then by E2, and then like that, okay? So this is the first one. This part is the I minus first one. And the last one is your last, well, ith one, okay? So you go from innermost to outermost in that order. Actually, this part is already available. No, let's change this, because I just noticed that this is already available. This is already available from the previous iteration. So you just multiply it with EI. That will give you the solution. Do we have time? No, I think we're out of time. So what I'm going to do is, well, let's stop here. I'm going to take the method from the beginning, maybe from step 1 next time, and then we'll continue, okay?